You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Cloud Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Compute allocation is one of the most critical aspects of designing a performant and efficient cloud environment. How central processing units, virtual CPUs, and graphics processing units are assigned to virtual machines directly influences cost, responsiveness, and scalability. In virtualized cloud systems, physical compute resources are abstracted and divided, allowing many users to share infrastructure. Understanding how this abstraction is managed, especially for CPUs and GPUs, is key to making informed decisions. For Cloud Plus candidates, this topic ties together resource provisioning, workload planning, and performance troubleshooting. The Cloud Plus exam frequently includes scenarios in which candidates must select the appropriate compute allocation model based on workload type or platform constraints. These scenarios might ask you to identify when a GPU is required, whether a vCPU count is sufficient, or how overallocation impacts performance. To respond accurately, candidates must understand how cloud platforms assign virtual CPUs, how they relate to physical hardware, and when dedicated or shared GPU models are appropriate. This episode walks through those models and highlights what makes each suitable or problematic. At the foundation of compute allocation is the physical central processing unit. A CPU core is a hardware component capable of executing instructions, usually one thread at a time, unless simultaneous multithreading is enabled. Each server has a fixed number of physical cores, and those cores define the physical limits of compute power available to a hypervisor. In traditional environments, workloads are scheduled directly on these cores. In cloud platforms, however, most compute scheduling is done virtually, which introduces new models and considerations. A virtual CPU, or vCPU, is a software-defined slice of a physical processor. Hypervisors expose vCPUs to virtual machines, scheduling them to run on available physical cores. A vCPU is not always a one-to-one mapping to a physical thread. Rather, it represents a time-shared processing slot. Cloud providers typically describe virtual machine sizes in terms of vCPUs, which allows for flexibility in scheduling and resource optimization. The way vCPUs are mapped and scheduled greatly impacts performance, particularly under load. When assigning vCPUs to virtual machines, cloud administrators must consider workload type, concurrency level, and hypervisor capabilities. A lightly loaded application might run smoothly on a single vCPU, while multi-threaded software such as databases, web servers, or analytics engines requires multiple vCPUs to operate efficiently. Over-provisioning virtual machines with more vCPUs than physical cores can lead to contention, especially if many VMs are active at once. This can degrade performance and increase response times. The hypervisor plays a critical role in managing how vCPUs are scheduled onto physical cores. It must decide when each vCPU gets time on the processor, ensuring fairness and efficiency. When too many vCPUs compete for too few cores, the result is contention, which appears as latency or application slowdown. Scheduling algorithms vary between platforms, but all aim to maintain balance and prevent starvation. Understanding how the hypervisor affects scheduling helps Cloud Plus candidates identify performance bottlenecks. GPUs operate differently than CPUs. A GPU is a specialized processing unit optimized for executing many operations in parallel. Originally designed for graphics rendering, GPUs are now widely used in data science, machine learning, and scientific computing. Cloud providers offer GPU-enabled instances that can be assigned to workloads requiring fast concurrent computation. These instances are typically more expensive but provide performance improvements that general-purpose virtual machines cannot achieve. GPU allocation models include shared access, virtual GPUs, and pass-through or dedicated GPUs. In shared models, multiple virtual machines use a common GPU, which reduces cost but may introduce variability in performance. Virtual GPU abstract portions of a GPU for individual use, balancing performance and isolation. Pass-through models dedicate the entire GPU to one virtual machine, offering maximum performance and hardware-level access. For the Cloud Plus exam, candidates should recognize these models and understand when each is appropriate. CPUs and GPUs are suited to different task types. CPUs are best for general-purpose, serial computation, such as handling transactions, logic processing, or control plane operations. GPUs, by contrast, excel at processing large volumes of data in parallel. Applications that perform vectorized calculations, such as matrix multiplication, deep learning inference, or real-time analytics, see significant benefits from GPU acceleration. Choosing between the two depends on understanding how your application consumes compute cycles. Dynamic allocation allows cloud platforms to respond to workload changes by adjusting vCPU or GPU counts. Some providers allow live resizing of virtual machines, while others require instance reboots. Auto-scaling groups can launch additional instances or shut them down based on defined thresholds, such as CPU utilization or queue depth. Monitoring and threshold tuning are critical to making dynamic allocation work effectively. Cloud Plus candidates must understand how to configure and tune auto-scaling policies to ensure reliable compute performance under variable load. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. The number of vCPUs allocated to a virtual machine directly affects its multitasking ability. If a virtual machine has too few vCPUs, it will struggle to handle concurrent processes, resulting in slow performance or application hangs. On the other hand, assigning too many vCPUs can lead to unnecessary contention and waste, particularly in oversubscribed environments. Striking a balance between core count, thread availability, and memory allocation ensures that applications run efficiently without overtaxing the host system or increasing costs. Most cloud providers impose usage quotas for vCPUs, often on a per-region or per-subscription basis. These quotas help maintain infrastructure stability and prevent resource exhaustion across tenants. When designing large-scale environments, administrators must monitor vCPU usage and request quota increases as needed. Failing to plan for quota limits can delay deployments or lead to auto-scaling failures. For the Cloud Plus exam, candidates must be familiar with how quotas affect provisioning and how to manage requests for expansion. GPU pass-through is one of the highest-performing allocation models. It allows a virtual machine to communicate directly with the GPU hardware, bypassing the hypervisor. This reduces latency and maximizes processing efficiency, which is especially important for real-time inference, 3D modeling, or high-performance simulations. However, pass-through reduces portability. Virtual machines tied to specific hardware cannot be live migrated easily. Virtualized GPUs offer a middle ground, enabling sharing while still isolating memory and compute slices for each tenant. Some workloads require multiple vCPUs or even multiple GPUs to function effectively. Data analytics clusters, distributed databases, and scientific modeling platforms often benefit from parallel compute resources. However, not all software is designed to take advantage of these configurations. Applications must be written or configured to spread workloads across available processing units. Licensing models must also be considered, as some software vendors charge based on core count or GPU utilization. Cloud Plus candidates should understand how parallel compute affects cost and software planning. Licensing and compliance remain essential factors in allocation decisions. Enterprise software vendors frequently tie their licensing models to the number of allocated vCPUs, or attached GPUs. For instance, assigning more cores than necessary may increase licensing fees or create a compliance violation. Similarly, adding a GPU to a workload that does not explicitly require it could trigger additional charges without delivering value. Administrators must map resource needs carefully to avoid unintentional over-provisioning and associated costs. To manage these risks, monitoring tools are used to track real-time usage of both CPUs and GPUs. Cloud dashboards often provide per-core and per-instance utilization graphs, while GPU metrics may include core usage, memory consumption, and temperature. These metrics inform performance tuning decisions and help identify whether resources are underutilized or saturated. Monitoring is not only a reactive tool for troubleshooting but also a proactive strategy for optimizing allocation and planning future infrastructure needs. Underperforming applications are frequently the result of mismatched resource allocations. A virtual machine may have too few vCPUs, leading to high CPU wait times, or it may be missing access to a GPU required for a specific task. Conversely, resources may be over-allocated, resulting in wasted capacity and unnecessary expense. Logs and metrics help pinpoint these mismatches, revealing where the bottleneck lies. Cloud Plus exam scenarios may involve identifying these misalignments and recommending appropriate right-sizing strategies. Allocation choices influence other parts of the architecture, including network bandwidth, storage throughput, and backup strategies. For example, a compute-optimized instance may offer high core counts but lower memory, making it unsuitable for database workloads that require in-memory caching. Similarly, a GPU-enabled instance may come with limited storage options or require different snapshotting processes. Designing compute allocations in isolation can lead to gaps in other subsystems. Cloud Plus candidates must be able to integrate allocation decisions into holistic architecture planning. Best practices for provisioning compute resources start with profiling the application's actual requirements. This includes running performance simulations under load, analyzing I/O patterns, and observing memory usage. Based on this profile, administrators can select the most appropriate allocation model and instance type. Regular review ensures that allocation decisions remain valid as workloads evolve. Monitoring must continue after deployment to detect shifts in behavior and performance. This approach ensures long-term alignment between compute resources and business needs. In summary, choosing between CPU, vCPU, and GPU allocation models is not a one-time task. It's an ongoing process that affects performance, cost, scalability, and compliance. Cloud architects must understand how virtualized resources are assigned and how they interact with application behavior. By learning the trade-offs between shared and dedicated hardware, between dynamic scaling and fixed sizing, candidates can design infrastructure that meets both technical and financial goals. For the Cloud Plus certification, mastery of these models is essential to answering exam questions and delivering robust cloud designs. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.